So if you try out a linear regression in R, you'll find to your surprise that it's exactly the same function that you used to do your analysis of variance. And so that's actually an interesting insight, that all these techniques that we covered are essentially all the same kind of analysis. So an ANOVA can be reformulated as a regression, an analysis of covariance as well, multiple linear regression. So these are all the same things. So that's interesting, and I want to just briefly explain to you why that is and how that works. And since linear regression and multiple linear regressions are also used as methods of discovery, where you just throw a bunch of variables at a problem and ask, is there an association between those variables? We also have to be careful about adjustment for multiple inference. So we talked about this earlier in the context of pairwise comparisons, and I also show you how to deal with it here in these kind of situations. So the way general linear models are implemented in R is with the linear model function, and that's exactly the same way as we've seen it for analysis of variance or for analysis of covariance. You just have your response variable stated as a function of your predictor variable or variables, and you can write this out in an object. I'm just calling this here out1, and instead of getting an ANOVA table out of it, we can just get a summary out of that, and that would give you the intercept and the coefficients of your linear regression that we have in this case. And so one thing you can do, and that's actually one of the main reasons why you want to do a regression analysis, is you can use that equation to predict y values from other x values that you may have in a different data set. So you have to make sure that the variable names match up, and then you can use the predict function and use the equation that you developed with one data set to make predictions based on your x values in another data set. So that's a very common application. You often have variables that you're interested in, but that are very difficult to measure. So what you do is you measure something else that's easier to assess and then make those predictions. So just to give you an example, as a forester, you always want to know, how many cubic meters of wood do I have in a forest stand, or what's the biomass of a tree. Those are very difficult to actually measure. You have to cut up a whole tree and weigh it to determine the biomass. You don't want to do that too often, but you can do it for a small sample of trees. So this is your .1 data set. And so once you've established a relationship with something that's easy to measure, for example, the diameter at breast height, you can just put the measuring tape around, and if that is well correlated to your biomass, then you can use a predict function to make that inference for the rest of the trees that are out there. And of course, you have to make sure that that's a linear relationship, so that is a linear model. If not, in the next video, we'll cover nonlinear regression equations. And instead of one predictor variable, you might develop an equation where the volume of a tree is not just a function of diameter, but also height. So that's called a multiple regression, and that can be also useful in some cases, as long as you don't have too many predictor variables, and as long as it's fairly simple and straightforward what those relationships are, that can be used as well. So in a multiple regression equation, those predictor variables are added with a plus sign. You can put a multiplier there. So what happens then is that x1 times x2 is added as another predictor variable to your equation. But normally this is the way you do multiple regressions. Now I mentioned earlier that this is exactly the same function that you used for ANOVA in R. So it's a general linear model. And you can think of an analysis of variance also as a regression problem. So if you have two treatments A and B, you can code them as 0 and 1, and then just do a regression. So if that is a significant correlation, that would also be a significant treatment effect. So the way you would do this, you could just convert your A and B to a 0 or 1, and you can run a simple regression, and it would give you exactly the same answer, the same p-value, as if you were to do an analysis of variance, just like we discussed it as a variance between versus variance within ratio with an f value and an f distribution. So these are mathematically actually identical. And you may wonder, well, what happens if I have a third treatment level? So what you do is you just create additional dummy variables, as many as are needed. So I can code, for example, a treatment A, B, and C with two predictor variables. So one dummy predictor variable here is x1, the other is x2, and then the treatments can be coded as a combination of those two. So A is a combination of x1 being 0 and x2 being 1, B is 0 and 0, and C is 1 and 0. So 3 treatment levels can be modeled as a plane. So basically the mean of 3 points fixes that plane, and that multiple regression can then again be used to derive an f-value that would allow you to test for statistical significance. So for 4 treatments, you would need to add another predictor variable in order to code it as dummy variable. So you would need x1, x2, x3. But in principle, you can code any kind of single or multi-factor analysis of variance that way. And the f-value in this case, the variance between over variance within, is simply the variance explained over the residual. So those are mathematically identical. So you can code any ANOVA problem as a multiple regression problem with those dummy variables. So abbreviations for linear models can be a little bit confusing because the general linear model is usually abbreviated as LM. So linear model or general linear model are synonyms. So regression, multiple regression, analysis of variance, or analysis of covariance all fall under the general linear model. And there's also something that's called the generalized linear model. So that's abbreviated as GLM. And that covers things like logistic regression, Poisson regression, or also, predictor variables can also be class variables. The important thing is that the error distribution is other than normal in the generalized linear models. So your residual does not have to be normally distributed. You can specify different error distributions. And you can certainly use multiple linear regression to make predictions of in a dependent variable based on multiple independent variables. But the analysis is a little bit tricky. It's okay if you really just have only a few predictor variables that have a clear influence on your dependent variable. But it's generally not safe to use as a data mining tool where you just throw a bunch of potential predictor variables at a problem to discover which predictor variables actually influence a response variable. So it's not a very good method to do that. I would not recommend it. So the problems are issues with collinearity. We talked about this before. So if you have multiple predictor variables that are correlated among themselves, it's very hard to actually interpret the coefficients. So what kind of inferences you draw from those equations. This usually goes horribly wrong. And I have yet to see an example where multiple linear regression is successfully used for those types of analyses. So there are much better tools out there that are more flexible, that are better set up to find out which variables matter, and that are also handling nonlinear relationships just fine. If you have a problem like this, just jump into those better techniques, for example, general additive models. Those are much better techniques to address those types of issues. So we'll cover those in an advanced multivariate statistics class. So and last but not least, I do want to talk about adjustment for multiple inference. And I'm going back to this interesting example here of sales of ice cream versus forest fire from that database in Maine. It's actually not a spurious relationship. So those are linked by a third variable. But the authors of this study, actually, they also found other interesting things. So for example, if you look at the divorce rate in Maine per 1,000 people, that's a red line here, that's highly correlated to the US consumption of margarine. Your inference would be, if you want to save your marriage, eat butter. So these are actually completely random and spurious relationships. They just pop up by random chance. So this happens for real. If you look at big enough databases and have lots of variables, you find things that look perfectly correlated, right? So this probably has a correlation of 0.95 and it means nothing. And the reason why this happened is exactly what we had before when we did the pairwise comparisons as a follow-up to analysis of variance. So if you run a bunch of statistical tests, you will find correlations that are significant. So also here, adjusting for multiple inference is critical. And the function that I suggest here is the p-adjust function from the R base package. So the way it works is if you have a bunch of p-values that come from either correlation analysis or any other test, you can just list them here, tell R how many there are, and pick a method for adjustment of multiple inference. You can pick Bonferroni, but Holmes adjustment, that's a sequential Bonferroni adjustment. That's a very good way to go about this. And what it does in this case, it will give you adjusted p-values that have higher values, and you can then interpret them to an analysis-wide alpha level that you're comfortable with. You can use 0.05 if that makes sense for your particular situation, and those would then be adjusted for an analysis-wide multiple inference for n equals 4 p-values. This is actually a nice paper that describes how the sequential Bonferroni works. So it's in Evolution, it's written for biologists, so I don't cover it here, but if you're curious, this is actually quite easy to understand. And he also makes a very nice case on what to look out for when analyzing tables of statistical tests. So you really have two kinds of problems. One is the multicollinearity, and then this one here is a multiple inference problem. So both are separate issues that converge here to make your life really difficult when interpreting tables of correlations. So he makes this case very nicely why that's important, and I'll do it too with a little R simulation. So this is my little program here to simulate how the relationships that tell you to eat butter to save your marriage come to pass. And so we just generate randomly values, 20 values for an x and a y variable. So let me do this, x and y, and we can look into this. So these are just 10 normally distributed random values, and I can look at a correlation between the two, and the expectation is that there's no correlation because these are just random values. And it is not exactly zero, it rarely ever is, or it never is. So in this case, we got minus 0.19. We can also test if that correlation is significant. So that's the next command here. And 0.4, so definitely not significant. Something like this could happen by random chance. Almost half the time you get something as big or bigger as that. And we can extract that p-value also from this statement here. So this is just a list of statements, and I want the third one. You have to sometimes try that out. So if I get the third one here, that is just the p-value extracted from that output file. So we can run this a bunch of times if we want to. So this time again, no significant correlation. I don't want to do this here manually, so I'm writing a little loop. I have a vector here that saves my R values, that's empty, and a vector that saves my P values, that's empty. And then I do this 10,000 times. That's exactly the same code that I had above here. And I'm just adding my p-value to that empty vector here. So let's run this 10,000 times, see what happens. So we can get the smallest p-value here. So that's quite impressive. That's a p-value of 0.00002 that just popped up just plain by random chance. So just like that margarine versus divorce rate example. So highly significant. Nobody would doubt this. This would get published if it's not as outlandish as this margarine example, and everybody would believe it for a while until it gets debunked by people who try to replicate this and it doesn't work. So these are things you have to always keep in mind when you do analyze larger matrices of multiple predictor variables and response variables. Those things pop up just by random chance. And it's compounded if it's an important topic and thousands of researchers work in this area and do these kind of analyses, then eventually these types of spurious correlations pop up. And that's in addition to the issue of collinearity and getting causal relationships wrong, right? So Whenever you see a headline in the newspaper that's based on this type of analysis, association analyses, discovered a gene responsible for something. Well, we're looking at tens of thousands of genes. So this is exactly what's happening here. And of course, they will do adjustments for multiple inference. But if you have enough people working on this never protects you fully from making those mistakes. So this happens 1 out of 10,000 times, and that's a study that gets published. So if you get something like this yourself and it seems implausible, trying to verify it yourself is probably not a bad idea.